Hello everyone watching this video. Today in this video we will discuss the rotational kinetic energy or kinetic energy of a rotating body. So here first we take a body and this body is rotating about this axis at the angular velocity omega. So here we are discussing the rotational kinetic energy and we have a body of mass m and this is rotating about this axis and its angular velocity is omega. And to determine the rotational kinetic energy for whole body, we consider some point objects or point mass on the body or in the body, and we determine the rotational kinetic energy for each particle, and we sum all the kinetic energy and we get the total kinetic energy for this body or total rotational kinetic energy for this body. For that we assume that here we have a mass m1 and the distance of this mass m1 from the axis of rotation is r1. We have the mass m2 and the distance of this mass m2 from this axis of rotation is r2. Here we have mass m3, here m3, and distance is r3. And here I don't take much time, I take any nth mass, which mass is mn, and its distance from this axis of rotation is rn. So here that's how we took all those masses separately and we determined the distance of all the masses from this axis. So to understand, we just took 4 points or 4 masses. The first mass, which is at distance small r1 from this axis, second mass m2, which is distance r2 from this axis, and m3, and that's how we take the mass m4, m5, and our final mass is or nth mass is mn. So that's how we will conclude that. So first we write the kinetic energy. The kinetic energy of first particle will be half m1 v1 square. So that's how we write the kinetic energy, half mv square. So first particle, the mass of first particle is m1. So we write here the m1 and we assume that velocity of this particle is v1. So but we have the angular velocity here for this body, so we convert this velocity into the angular velocity. So angular velocity is right here v equals to r omega, v equals to r omega. So we replace here the velocity v. So kinetic energy for first particle will be half m1 r1 omega 1. That's how we write the kinetic energy for first particle. And here now we write the kinetic energy for second particle, which is half m2 r2 omega 2. Okay, and sorry, this is the square of velocity, so we write r1 square omega 1 square r2 square omega 2 square. And that's how we keep on getting all those kinetic energy. And kinetic energy for nth particle will be kinetic energy n, that will be half mn rn square or and omega n square. So these are the kinetic energy for all those particles from first to n particle. And when we add all those kinetic energy for individual particles, we will get the total kinetic energy for this rigid body. So total kinetic energy for this rigid body will be the kinetic sum of all the kinetic energy or summation of kinetic energies. So I write down that kinetic energy for this body will be first the summation of these all the kinetic energies. So the kinetic energy for first object is half m1 r1, and sorry, I wrote again, made the mistake. All those angular velocity for all the particles is same, so this will be omega only. So this is omega square plus this is the kinetic energy of first particle. Now the kinetic energy of second particle m2 R2 omega square plus we add the kinetic energy of third particle and we keep on adding till the kinetic energy of last particle, which is half mn Rn square omega square. So here we know that in all those expressions we have something common, the half and omega square. So we take half and omega square common and take that out. So kinetic energy will be half. Here we can write m1 r1 square plus m2 r2 square plus mn Rn square, and here omega square is out. So here this is m1 r1 square plus m2 r2 square and mn r square. We can write in the different form, which is kinetic energy equals to half summation of mi ri square and I from 1 to n and here omega square. So this is the formula. You can understand something. This is the mass and this is the distance square. mr square. So mr square, this is the formula for moment of inertia. So kinetic energy will be half I omega square. Half I omega square. I is the moment of inertia of this body about this axis and omega is the angular velocity of this body, and this is the half. So kinetic energy for this body about this axis will be half I omega square. So this is the formula of kinetic energy for any kind of rigid body rotating about any axis at angular velocity omega is half I omega square, where omega is the angular velocity and I is the moment of inertia about the axis of rotation. So here this is the formula. Now we can compare this formula field for linear kinetic energy and kinetic energy of rotation. In the linear motion, we know the formula of kinetic energy is half mv square, and in rotation motion we have the formula half I omega square. We converted m into I and v into omega. We know that in the linear momentum we have the mass or inertia, and in rotational motion we have moment of inertia. In the linear momentum, linear motion we have the velocity, and in the rotational motion we have the angular velocity. So the formula is same. In the linear motion we have inertia and velocity. In the rotational motion we have moment of inertia and angular velocity. So formula for rotational kinetic energy in the rotational motion is half I omega square. That is like the formula in the linear motion. And in the previous video we discussed that this is the symmetry, or this has some relation between linear motion and rotational motion, like in the linear motion and rotational motion. In the linear motion we have mass, here we have moment of inertia. In the linear motion we have force, here we have torque. Linear motion we have velocity, here we have angular velocity. In the acceleration, the angular acceleration, and now the kinetic energy. This is the kinetic energy for linear motion and this is the kinetic energy for rotational motion. So that's how we conclude our today's topic, and now we move forward with the next topic in next video. Until that, best of luck.